It was going guys, xiangqi here. Earlier I had some attempts to write a chess program in 6502 assembly and run it on my Q1 emulator that I made before that. But the problem with that was that I didn't have a complete picture of how exactly the program should look like. I mean, I had a prototype. I thought I had a prototype in C. However, there were really lots of significant issues with that prototype because, first of all, it was using signed integers. And yeah, recently, I just yesterday, basically, I had a discussion with Harmgert Miller and Talk Chess, and I was trying to explain that the way how this memory cells work in Q1, like wrapping around, it fixates FF on top and 0 on the bottom, then I don't consider this to be the signed integers and the signed arithmetics respectively. And he was saying that since the carry flag and the negative flag are being affected, this still can be treated and should be treated like as the signed arithmetics. And moreover that, then it's just a matter of how you handle the overflow. But there is no like standard overflow handling for that sort of a thing. So I decided to go a completely different way, and instead of dealing with those overflows of the integers, I decided to use only the highest bit to use as the signed bit, just like they do in like normal implementations, but without any ones or twos complements at all, completely. So the maximum value that I can have is 127, right? So 0x7f in hexadecimal. And if there is this, if the highest bit is set to 1, then this is going to be negative number. If it's not, then it's going to be the positive number. And I've implemented the entire evaluation function and the eninge maksymkorzh using this kind of logic. So now I have a prototype that kind of works, that can be kind of directly ported to 6502. So this video, I'd like to demonstrate, well, first, probably let's have a look at the source code. So here I have this proto.c. So yeah, I've managed to get rid of the signed variables. So the idea is, now when you have a look at the implementation, you might be wondering like, what the heck is that and why to do this ever? So let me explain this a little bit. So the idea is that I'm gonna be, just to give you an idea, let me take my smartphone. So here I made a mobile version of this. So here is the desktop version, and here is the mobile version of my Q1 emulator. And if the desktop version, we still can like write an assembly, use the fancy hexdem to see what happens in the memory, so extensive debugging features. And again, like just writing an assembly, you don't need to care about the memory offsets because the labels will calculate them for you automatically. But I think that's cheating. And I already tried that, and the problem is when you're using these fancy tools, it's still like you're writing, it's not even in CS, you're writing an assembly, but you're writing like a normal code. So the process of writing code doesn't change. That's what I mean. But when you try to actually code something using this thing, and when the only reference you have is the 6502 opcodes and QMROM routine shortcuts, like where exactly, like what addresses to call to get a certain behavior, like for IO, for instance, like to print something on the screen or take the input from the keyboard, that's going completely different. So that's completely different experience. And what I want to do now, I know it's much harder compared to actually writing an assembly, but I actually want, so since I have already the working prototype, I just want to develop this directly in machine codes in order to improve the design of how exactly I manage that. Because if I'm going to be writing this in assembly, here is the problem. So if I start writing this in assembly, I'll take the function and I try to do what C compiler does. So try to generate code to convert this C code into assembly, but just doing this by hands. And one of the major issues with that approach is that it will result in really huge code. I already tried that and just probably running out of 1K of unexpanded key memory, even though my emulator has way more. But anyway, just ultimately, like if I managed to fit this into 1K of memory, that would have been fantastic. But anyway, so just blindly doing the compiler job here, I don't want to go for this. So I'm gonna be using the prototype just to as the main direction of how this should be, and then actually do this in a good old school way. Like I had an interview with Bob Lidham, who's the author of King Venture, one of the that's an adventure game for King 1. It's like very old school, very epic to say the least. And when he was telling me like what was the development process look like, that's something absolutely different. And the reason why I'm doing this, I really want to experience this old school development process. I don't really care about the end result really, even though I put a lot of effort to make sure that the end result will be working properly without bugs. But anyway, I just really want this experience. I want to experience the old school development process. So that's the reason to go the most hardcore way possible, like going directly into the machine codes programming using the mobile version of my emulator, right? So and by the way, that mobile version is just another HTML, so it's not an Android app or iOS app, it's just an HTML. So yeah, that's another good thing. So this means that the only reason why I need this prototype is just to make sure that I know how to implement logic. But when it comes to the particular implementation of, say, this part, which returns evaluation dependent on site to move and whether to return the positive or negative score, I think that if I'm going to be writing this in assembly directly and even more in machine codes directly, since debugging is very hard when you don't have the memory dump, when the only way to debug is either single stepping the program and original King 1 did allow that, or otherwise if I just go for put in some break statements and then inspecting the machine context, like literally what are the values of the certain registers at this particular point, or even more important, of the variables that should be, like, say I made a move, just to make sure that I know that in the certain squares I need to have certain values, which means that the piece has moved. So in order to keep all this tracked, it's really important to divide and conquer so hard that, like, dividing to very lot of, like, smallest pieces possible to keep track of them. And I think that so first, this, like, from top to bottom approach, I just made it whole, and then we'll see how this goes. But now I want to go from bottom to top. So since I know the overall direction, I'm not really sure how exactly I'm going to be actually developing. This is the most challenging, this is the most interesting part, and this takes ages probably. But anyway, that's really interesting, and that's really exciting. So, sorry for talking for too long about this. I know most of those watching this video probably don't really care about this, but anyway. So here is the source code. So one of the core things to pay attention to. So all the data types are unsigned 8-bit integers. So just like those we have in a King 1. And again, like Harm says that those are signed. So it's not about, don't want to argue about that, but what I want to say is eventually all the values that this program operates on are from 0 and to 100 and to 255 or to hexadecimal FF. So within that range, all the values for evaluation or for move offsets, for whatever, all the values are within that range. So from 0 to 255. So just 8 bits need to represent that value. And if it comes about representing the negative value, I'm using the highest bit as the flag that flags that there is a negative value. And then I do the comparisons respectively. Then I do the comparisons respectively. So, like, if it's greater than 0, then the modules is like one bigger than another. If it's negative, then the sign goes otherwise, because it's approaching towards 0, which in this case, like, it's abstract 0. But anyway, so let's just keep going. So the next thing, so here I have the basic hexadecimal 88 board representation. So the left part, just you know this really nicely, guys. So here we have the chessboard, and here we have the p-square tables, like for obtaining the positional scores. So the challenge was to make the evaluation not exceeding the half of 255, which is 127, let's say. So I need to make sure that if one side has all the pieces, and if one side has a positional advantage, that this value will be no bigger than 127. So in order to achieve that, I actually made the numbers really small. So here are the values for the pieces. I could have made them like actually. So this is the pawns. This is the knight, bishop, rook, queen, and king is 0. So I could have made pawn equal to 1. But in this case, if I also want to use the positional scores, like 1 for pawn and 1 for putting a piece there, it would be sacrificing pawns for putting the pieces on the certain squares, which is not good. So I need to make sure that the piece values are at least slightly bigger than the positional values. So the positional value is 2 for central squares and 1 for just the next ring around the center. And then, so pawn is worth 3, then like 3 times by 3 is 9. These are the knights and bishops. Then 5 times 5 times is 15, and this is rooks, and 1b is 3 by 9, so like queen worth 9.9 pawns, and each one pawn is 3, so 3 multiplied by 9, 27, and in hexadecimal this is going to be 1b. So I hope I didn't just make any mistakes now while trying to explain this. All right, so and this course results in a game where engine plays itself at the depth 3, and it results in a checkmate. I'll show you that game just a little bit later. And here are the move offsets. So here know that where the first is 8. This means it's not really, it's like the first bit is being signed up. 9 the same, so the first bit is signed up. I just see this number is already converted to binary in my brain, so yes, maybe. So if you don't see this, you just try to convert this values from hexadecimal to binary in calculator, for instance, and you'll see like the highest bit being set in here, like here. So where the 8 or 9 or A, yes, here as well. So here is like 0 1 0 1 0 0 0 1. Yes. Okay, so then here we have the variables. So all these are kind of static, so they just defined and then used. But what is more challenging, so the next challenge I'm about to encounter is I need a bunch of variables that would be in a stack frame, which means that they would be related to a certain depth. And I really hope that I won't run out of stack in my implementation, because Scheme 1 only have 200 and 255. Yes, 255. It's one memory page for a stack. So yeah, oh my god, 255 bytes, right? Yeah, 255 bytes. That's correct. It should be fine. So yeah, I still need to calculate it. But again, now this is gonna be like, this was from top to bottom, and now this is gonna be from bottom to top. This is gonna be a completely different approach. But anyway, the logic itself is exactly the same in my bare as it was in my bare minimum chess program in C, and I've reused it significantly. A part of having this different scores, part of having all the evaluation values from 0 to 255, and that's pretty much all the changes basically. So what we do here, so here is the evaluation function. So in case if it runs out of depth, it needs to return the static evaluation score. So the evaluation here, so we need to obtain the material black and positional black, right? And then basing on whether the material black and positional black and positional white as well as positional and material white as well. So if those are positive or negative, we need to make sure we need to make sure that we return them with the right sign, because the eninge framework assumes positive score for white pieces and negative score for black pieces. So in order to represent the negative score, I just do this bitwise ORing with the highest bit. So hexadecimal 80 is just the highest bit. It's in binary. It's like 0. It's 1 0 0 0 0 0 0 0. Yeah. So that's how it works. So I do either assign this one or just and so this is the negative number and this is the positive number, and the same here. This is the positive number, this is the negative number. And then when it comes to actually returning, so I did this code yesterday, but already don't remember how exactly I did it, because it was just I've been replacing this like portion by portion until it works. So yeah, this should be just fine. So depending on the side to move, I do either, so here is like plus, this here we have this minus, so well, just separately for material, separately for positional, separately for white, separately for black. But anyway, what is interesting here is that this evaluation eventually, so when it reaches 0, it returns here. So here the score would be the value from 0 to 255, and it might be it might either have highest bit set, and in this case this means that the value is negative, or it might not have it set. In this case this means that the number is positive. So what I do next, I check for this. If this has a negative number, then I swap it. So this is the negation in the eninge. So in the regular framework you just say score equals minus search. So to rewrite this, we can say score equals search, then score equals minus score. And this is the representation of line like score equals minus score, but using this sign bit that I used. So here, if we have a score that is currently negative, then we'll make it positive. And otherwise, if it's positive, then we'll make it negative. So we just kind of swap in the sides. We swap in this bit. So it's like, it might be treated as an XOR operation for a single bit, for instance. So yeah, what next? What next? Just wondering, still need to make sure if I can make this somehow with XORing or not, but yeah, just forget that. So yeah, just make and move, unmake and move. Don't forget to change the sign every time. So this would be like 24 minus sign of decimal, because the sign is either 8 or 16, and the 8-bit, the 16th bit that's just made for easier distinguishing, like whether the piece depends regards to the side to move or not. So this has been covered hundreds of times, thousands of times before. Yeah, a real lot of times. And then this part is interesting. So this is actually the brute force eninge search. So generally what we're interested in, so if we found a better move, then we want to update, so we want to make the best score equals to our score. And both are unsigned, so both are from 0 to 255. So the problem is how to find this, if this is better. So here is the bunch of comparisons I do for this. I know probably it looks ugly, but at very least now I know how to make this using the 652 machine codes, because the logic is clear and straightforward. There is an infinite number of possibilities to mess up something, but yeah, so if you just split this, then maybe it would kind of make sense. And again, when I'm going to be writing this in assembly, maybe I just, since assembly allows these jumps, like you can see this would be like go to, we don't use it here. So probably I could just avoid doing some like duplications in the code. So probably I'll try to like make it smaller, because when it comes to when you're trying to write C as you're trying, as if you've been writing an assembly, it turns that C code grows significantly. Not sure if that works in the country as well, so I need to think about this. But anyway, so this is kind of it. And finally, I just have the print board functions just for debugging purposes, just to make sure, just to enjoy the game, enjoy the show how the game goes. And here is the driver which makes it play in itself. So if you want to try to compile and run this, you can use GCC for this purposes. If you run Windows, most likely Unicode is not going to be working for you this way, so you can just command out this part and command out this and command this part and command this line, and then uncommand this one and uncommand this one. And instead of Unicode pieces, you would be having like the ASCII characters available here to represent the chess pieces. All right, so let me finally demonstrate how the game goes. So and here we go. So black starts with d4, and here we go. You know that the game is quite interesting. So say like white is forking. And assuming that this engine doesn't actually have quiz and search, this actual game with this particular scores, I personally really like how it looks. So say like, so actually just a little bit spoiler, a bit of a spoiler ahead. So black are these guys. These guys are white. So maybe not really nicely shown, but if you just invert the colors, then this would be exactly black and this would be exactly white. But anyway. So black is going to win this game. So you see, like now black is facing an issue of losing a piece basically. So it sacks a pawn, right? It sacks a pawn. So sack is accepted. Hold on a sec. Oh my goodness! I thought it just. Oh my goodness, I thought it just made a move twice for one side, and I was like, oh my god, what's going on? Fortunately not. So the rook moves from h8 to g8, threaten the bishop. So far so good. Then bishop takes the knight, right? And pawn takes. And now black is going to be pieced down because the next move, this bishop is captured. So currently, black is pieced down. But you just have a look how this goes further on. This is really interesting. So white keeps developing. So check. So using the weakness of this squares, and this is a double attack. So just it kind of attacks the bishop. So if not careful, if it just steps aside, then white is gonna win this bishop back. However, this is nice defense, so protecting from check. Meanwhile, protecting the bishop, so brilliancy. I didn't see where the move was made. Yeah, so pawn goes up. Pawn is pushed. So pushing the pawn to attack the rook, right? It's taken. Again goes here, and now the rook is forked. So now it's about to be losing the rook. What a fantastic thing. All right. And it attacks. And it seems like black is in a bad situation now. So it seems like the white is not only going to actually return his material back, but also have an advantage, have an exchange. Yeah, have an exchange, rook for a bishop at the very end. But we got to check. So king steps aside. Now here, yeah, probably. Well, I'm not sure. I'm not really sure why this knight move is considered. I'm not really sure. So probably just take this rook. There is no mate here so far. There is no mate here. So yeah, from the chess perspective, it might not be perfect, but yeah. So he goes, threatens mate here. All right. So what was the move? Okay, and already. Okay, just hold on a sec. Here it is. So actually, this move yeah, this move results in a check, so it's forced to go out, right? And the next move, actually, this is mating. You see, like, what a fantastic mate. Yeah. Oh my god, guys. So I don't know. I think that for such a tiny program, it's quite an impressive game, to say the least. And if I ever manage to run this on Kim 1, even though it's gonna be an emulator, anyway, I think this is gonna be incredibly exciting. So yeah, at the very least, now I have this prototype. So if everyone is interested in having a chess program that doesn't rely on a signed integers, Harmgerd Muller, sir, I'm sorry for calling this kind of unsigned thing, for this mess up, signed versus unsigned. But my understanding is just probably a little bit weird. But anyway, so yeah, if anyone is interested, then feel free to play around with this kind of program. And yeah, so it's really intended, like, not to be beautiful, not to be like playing nice chess, but trying to be as assembly port and friendly as possible. So if I ever manage to bring this to the next stage, I'll be happy to share that in the video as well. That's it from my side. Thanks for watching. Until the next time, and take care.